Hi, I'm Corin, CEO and co-founder of Rowan, and in this video, I'm going to walk through tautomers, what they are, how to run a tautomer search on Rowan, and how to interpret the results. First off, what are tautomers? So tautomers are groups of molecules that can readily interconvert under fairly normal conditions. Most commonly, this means compounds which can interconvert between each other by switching protons. These are prototopic tautomers, like ketones and enols. There are other forms of tautomerism, like the ring chain tautomerism exhibited by some sugars, but we're not going to talk about that more in this video. That's much less relevant for most cases. One example of a nice tautomeric molecule here is 4-pyrimidone. So you see the molecule as drawn is in sort of what we call the, one of the NH tautomers because the proton is sitting on an N. But we could also imagine the proton sitting on this other N and shuffling this double bond around, or even sitting on this O to form sort of the OH tautomer. And when you're faced with a molecule like this, in this case, we sort of can guess that this is the relevant tautomer because it's the one that's on the Wikipedia article. But it's not very obvious from first principles how to necessarily guess where the protons will prefer to sit. It can be pretty sensitive to the exact steric or electronic effects in a given molecule. So it's nice to be able to run a calculation to try to get an estimate for what will happen. So let's try it out on this compound, since we already sort of know the right answer. We can copy and paste the smile string and head over to Rowan, where we can click the new tautomer search button from the main page. And we can input this smile string. So we can say 4-pyrimidone. Submit, and there's our molecule, just like we saw it on Wikipedia, with the proton sitting on sort of N, I suppose this is N3 in the nomenclature. Okay, and now we have very little to do to run the tautomer search. The only thing we have to select is the mode, which essentially tells us how we're going to generate the conformers of each tautomer. And in most cases, careful is appropriate, unless you're really trying to run this on a big library. So we'll say submit tautomers. Let's talk about what's happening behind the scenes while this runs. The Rowan tautomer search code is going to iterate through all potential tautomeric sites. It's going to try to find the places that are reasonable to add or remove protons, and then it's going to run a conformer search and geometry optimization on each of these sites, and then compare the energy of all the different tautomers. In the end, this gives us an output like this. So we see the lowest energy tautomer is number 1 here, which indeed puts the proton on N3, like we saw on Wikipedia. The second highest energy tautomer is the OH tautomer, and then the highest energy tautomer is this N1 tautomer. It's labeled as N5 here, but if we follow the proper sort of pyrimidine nomenclature, this should be nitrogen 1. And so we can see from this output that the relative energy is shown here along with the weight. So this lowest energy tautomer has a relative energy of 0 because it's the lowest. The OH tautomer is like 1.3 kcals per mole above. So that's about a 9-to-1 ratio that's predicted. And then this N1 tautomer is very high in energy, almost 5 kcals per mole above the ground state, and is predicted to have really almost no population whatsoever in solution. And so if we were trying to engineer a drug in which we wanted, one of these tautomers, it'd be helpful to have these results. So if we think there's a key interaction that this NH is making, for instance, we could feel pretty confident that this is an accessible tautomer. Whereas if we expected this NH to make an interaction in a binding site, we might be pretty disappointed by the results we got back. So let's try this on another compound, just to showcase sort of how different electronic effects can impact tautomeric populations. So we can take this molecule, we can resubmit it. We'll resubmit as a tautomer search. And now let's say we'll do 2-fluoro-4-pyrimidone. So we'll throw fluorine in there, which we should sort of expect will probably have some sort of impact on the different stabilities of these different tautomers, although we might not be able to guess sort of ab initio what this might have. So actually, if you want to pause the video right now and think about what effect you'd expect this to have, go for it, and we can see if your intuition was right or not. Okay, I'll go ahead and submit this, and it's going to run right away, which is lovely. And so now we can see, in this case, we resubmitted from this tautomer, sort of the N1 tautomer, but it doesn't matter because Rowan will search through all of the tautomers, no matter the input structure. So it's not important to resubmit from any given tautomer. And there we go. And here's the answer. Did you get it right? So now the lowest energy tautomer by a lot is predicted to be this OH tautomer. The tautomer which was previously favored, the sort of N3 tautomer, is now about 4 kcals per mole higher in energy. And the N1 tautomer is now like insanely unstable, so almost 8 kcals per mole above the ground state. And it's worth thinking about why this might be. So this perhaps is a little bit of a surprising result. But I think what we can think about in trying to interpret this is that, in this case, OH is, not a super electron withdrawing group. It sort of depends on exactly where you are. But in general, we think of, OH or OR substituents as somewhat electron donating. But in these other two cases, we have this sort of, CO, this carbonyl, which we do think of as quite an electron withdrawing group. And so my interpretation of this is that when we sort of add this extra, very electronegative atom that we're adding on here, we're actually sort of destabilizing other electron-hungry groups on the ring. And so, as a result, we sort of destabilize anything that has a CO double bond and stabilize anything that has a CO single bond, just because, everyone's able to sort of get their preferred electron density a little bit more easily in this case. I'm not sure if that's the right way to think about it. There might be a more intelligent or more mathematical way to think about it, but that's how I interpret these results. Anyhow, thanks for watching.